Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's get started on our set of questions for today's session. Okay, so question 1 asks, what is the freezing point of water? Okay, so the freezing point of a substance is when it goes from its liquid phase to a solid phase, and it's at the freezing point where they can coexist in equilibrium. So for water, this is that in between where it's water and ice. Okay, so for the freezing point at water, it is 0 degrees Celsius. So when the temperatures are greater than 0 degrees Celsius, our water is in its liquid form, and when it's below 0, like in the negatives, this is when you have ice or snow even. And the junior tutor said that the freezing point is defined as the temperature at which solid and liquid phases coexist in equilibrium. The normal freezing point of a substance is the temperature at which a substance freezes at 1 atm pressure. This can be co-defined with melting point of a substance, where the substance changes from a solid to liquid. Every substance has its own freezing point, determined by experimental observations. So for water, the freezing point is at 0 degrees Celsius. Okay, so this solution is correct. Okay, so question number 2. What is the electronegativity of oxygen? So first, let's define what electronegativity is. It is the capability of an atom to attract an electron. Okay, so for oxygen, we can look at a periodic table that shows all the different electronegativity values. So here's one for example. You can see that oxygen's is 3.5, which is relatively high. So 3.5, if we compare it to the other values, is pretty high. And you'll see that the highest electronegativity value is fluorine, which is 4. So because oxygen has a high electronegativity value, this has a great effect on some substances that contain oxygen, and the most notable is like water. So here's a molecule of water, which everyone knows to be H2O. Because oxygen is more electronegative than our hydrogens, it attracts the electrons more than the hydrogens do. So this causes a dipole moment in a water molecule, and oxygen, since it pulls the electrons more than the hydrogen, there's an uneven sharing of electrons. So this causes a partially negative side of water, and the hydrogens being partially positive. So this is why water is polar. Due to electronegativity of oxygen. And the hydrogens aren't electronegative enough to balance out oxygen. And the fact that there are the two lone pairs makes the water molecule bent. So that's why it's not symmetrical and why water is polar. Okay, so the junior tutor said that electronegativity is a term coined for the capability of an element to attract an electron density to them. In the periodic tables, the electronegativity value of each element is given. Well, yeah, in some periodic tables, it can just be given. And you can see that as you go right, or as you go up on the periodic table, the electronegativity increases. This is because the elements on the right tend to take away an electron when they form a bond for them to achieve stability. Using the periodic table of elements, the electronegativity value for oxygen is around 3.44. Okay, so this solution is correct. So depending on what you use as a reference, you might get slightly different electronegativity values. So you can tell that this one here is a little more accurate than the table that I used, which kind of like rounds the values. So it just depends on which reference you use. But this solution is still correct. Okay, so question number 3. Determine whether each molecule is polar or nonpolar. So let's write out all the Lewis structures for each of these molecules. So when writing out Lewis structures, we need to find out the total number of valence electrons for each of these atoms. So sulfur has 6 valence electrons, and chlorine has 7. And since there are 2 chlorine atoms, we multiply this by 2. And when we add these values up, we get a total of 20 electrons. So first, let's draw out a skeletal structure of sulfur bonded with 2 chlorines. So the reason why I picked sulfur as my central atom is because it is lower in electronegativity than my chlorines, and also because it's able to form multiple bonds. So chlorine typically only forms one bond. And I can also draw in all of the lone pairs on my chlorine atoms as well. So if I count out how many electrons I've drawn so far, and I recall that each bond contains 2 bonding electrons, then I have only drawn 16 out of the 20 electrons I need for this structure. So for the remaining 4, I'm just going to place them as lone pairs on my central sulfur atom. Okay, so when we want to find out whether a molecule is polar or nonpolar, we first need to find out if any of the bonds in the molecule are polar. So to do that, I need to look at the electronegativity difference between sulfur and chlorine, just so we can see the the polarity of these bonds. So here's an electronegativity value periodic table, and if we find chlorine, sorry, it has an electronegativity value of 3, and chlorine's electronegativity value is, sulfur's is 2.5. Okay, so the difference between them is 0.5. Therefore, the bond is polar, and we know that because our electronegativity value is greater than 0.4 but less than 1.69. Okay, so now that we know that the bond is polar, we can draw dipole moments going towards the direction of the chlorines. And you'll notice that the molecular structure of sulfur dichloride is bent. So we have a bent structure, and it's due to the 2 lone pairs that are on our central sulfur atom. So since we have a bent structure, our dipole moments don't cancel out. So therefore, this molecule is also polar. So if we draw a net dipole moment, it kind of goes down like this. And we can say that we have a non-zero net dipole moment. Which tells us whether or not a molecule is polar or not. So if we had a 0 net dipole moment, then we'd know that it is nonpolar. Okay, so that's for part A. And now let's analyze our second structure, which is sulfur tetrachloride. So again, we need to calculate the total number of valence electrons, sulfur having 6, fluorine having 7, multiply the 7 by 4, and we get a total of 34 valence electrons. So again, I'm going to write my sulfur as my central atom, and then just 4 bonds to my chlorines, and I'll draw in all of the lone pairs. Okay, so if I count out how many electrons I've drawn so far, I only have 32 out of the 34 that I need for this structure. So my sulfur is going to have an extra pair of electrons on it, like so. So again, we calculated the electronegativity difference between sulfur and chlorine, and we know that it is polar. So if I kind of redraw this structure to kind of give a more accurate depiction of the molecule, the lone pairs would be like that, And then all my chlorines would be attached like this. And you can already kind of tell that we have a non-zero dipole moment again because of the lone pairs on the sulfur atom. So again, the dipole moments do not cancel out. So therefore, this molecule is also polar. So now let's look at our last structure, which is bromine pentachloride. And let's calculate the total number of valence electrons. So bromine has 7, and chlorine also has 7. And since there are 5 chlorine atoms, we multiply this by 5. And if we were to add these up, we get a total of 42 valence electrons. Okay, so now let's draw out its skeletal structure. We'll have bromine as our central atom. And then I'm just going to draw my 5 chlorines around it like this. And show all of the lone pairs. Okay, so if I count out all the electrons I have so far, I only have 40 out of the 42. So I need to draw my remaining 2 on my bromine. And this is kind of similar to our previous example, where our central atom only has the 1 lone pair. So again, we have a non-zero dipole moment. So let me sketch out a more accurate depiction of its structure. We have the lone pairs up like this, and we have the 5 chlorine atoms pulling at the bromine. Then again, we have a non-zero dipole moment. So therefore, this molecule is polar as well. So now let's see what the junior tutor said. We first write the Lewis structure for each molecule, then using the Vesper theory, determine the molecular geometry and polarity of the molecule. Okay, so they have the correct Lewis structure, and notice that their dipole moments do not cancel each other out, therefore this molecule is polar. For the second molecule, they also have the correct Lewis structure, and shown that it has a seesaw molecular geometry, and that they're arranged asymmetrically, so the dipole moments don't cancel out, so therefore this is polar as well. And the same thing goes for our last molecule. This has a square pyramid molecular geometry, which is arranged asymmetrically. So this solution is correct. Okay, so on to question number 4. Consider the ion HCO3. Draw the Lewis structure, label all the formal charges, write all the resonance structures, and label the hybridizations on both the carbon atoms and oxygen atoms. And what are the electronic shape and the actual molecular geometry around the central atom of this ion? Okay, so this question has multiple steps. So first we just need to write out the Lewis structure. So this will help us answer all of the questions. So we need to calculate the total number of valence electrons for this ion. Hydrogen has 1 valence electron, carbon has 4, and oxygen has 6. And since there are 3 oxygen atoms, we multiply this by 3. And also notice that the overall charge of this ion is -1, so we need to add an additional electron to this count as well. So if we count out how many electrons are in how many valence electrons are in the structure, we get a total of 24. Okay, so now let's try to draw out a plausible skeletal structure for this ion. We could have carbon as our central atom. And then I can draw single bonds to each of the atoms. So notice that carbon already has a full octet, but if I were to calculate the formal charges of all of these oxygens, they would all have a negative charge. So therefore, I know that my hydrogen would most likely be bonded to one of my oxygens like this, and that one of the oxygens will have a double bond. So let's draw the double bond here. And we'll verify that after drawing all of the electrons that we have the correct number of valence electrons, which is 24. So if we recall that each bond contains 2 bonding electrons, we have 1, 2, 3, 4, 5 bonds, so that's 10. And then counting out all the lone pairs, we have 24 in total. Okay, so this is a plausible Lewis structure for this ion. And we also need to label all the formal charges. So let me write the equation for formal charge up here. So formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So now let's calculate the formal charge of, let's say, the hydrogen atom. Hydrogen has 1 valence electron, and since there are no lone pairs on hydrogen, we write 0 non-bonding electrons. And there's only a single bond to hydrogen, so we write 2 bonding electrons divided by 2. We get a formal charge of 0. And let's do the same thing for the oxygen that has the hydrogen attached to it. There are 6 valence electrons in oxygen, and this oxygen has 4 non-bonding electrons, and there are 2 bonds to it. So we write 4 divided by 2, and its formal charge is also 0. For the double bonded oxygen, there are 6 valence electrons, 4 non-bonding electrons, and again 2 bonds to it, so we have 4 bonding electrons divided by 2. It's also 0. And for the single bonded oxygen, there are 6 bonding electrons, or valence electrons, and 6 non-bonding electrons, and only the single bond. So its formal charge is -1. So I can show that on my structure like so. And let's also just calculate the formal charge of the carbon, just so that everything is complete. Carbon has 4 valence electrons. There are no lone pairs, so it's 0. And there are 4 bonds to the carbon, so we have 8 bonding electrons divided by 2. So carbon's formal charge is 0. So the only negative charge is on our single bonded oxygen, and this is what causes the negative charge for our ion. So now we need to draw the resonance structures for this ion as well. And we have a hint that there are 2 structures in total. So pretty much the single bonded oxygen and the double bonded oxygen can be swapped. So we can have a single bonded oxygen at the top here with the negative charge. And the bottom oxygen can have the double bond. Okay, so these are the 2 resonance structures. And now we need to label the hybridizations on both oxygen atoms and the carbon atoms in one of the resonance structures. So let me write out on the side here the different charge clouds and whether or not they are sp, sp2, or sp3. So a charge cloud can be either a lone pair or a bonded atom. Let me label my different sections here. So this is part C, and this is part D, or being B. And up here is part A. Okay, so we know that a charge cloud can be either a lone pair or a bonded atom. So when we have sp3, this means that there are 4 charge clouds. sp2, we have 3 charge clouds. And sp, we have 2 charge clouds. So now we need to label the hybridizations of each of the atoms. So first, let's look at the single bonded oxygen with the hydrogen. It has 2 bonded atoms and 2 lone pairs. So this makes 4 charge clouds in total. So this is sp3. And the carbon only has 3 bonded atoms. So the carbon is sp2 because it only has 3 charge clouds. Now let's look at the oxygen. It has 1 bonded atom and 2 lone pairs. So it's also sp2 because it only has 3 charge clouds. And for the single bonded oxygen down here, we have 3 lone pairs and 1 bonded atom. So it is sp3. And we can also label the ones up here as well, but it'll just be the same thing. sp. And now for part D, what are the electronic shape and the actual molecular geometry around the central atom of this ion? So if we pay attention to our central atom, which is the carbon, we can see that there are 0 lone pairs and just 3 bonded atoms. So if we use a Vesper theory table, this can tell us the molecular shape and electron geometry. So when we have 0 lone pairs and 3 bonded atoms, we have a trigonal planar molecular shape and electron geometry. I'm just going to write trigonal planar for both. Okay, so this answers all the questions. So let's see what the junior tutor said. They have the correct Lewis structure and drew out the resonance forms and labeled each of the carbon and oxygen atoms. Yep. And they found that according to the Vesper theory, they have a trigonal planar molecular shape and electron geometry. So this solution is correct. Okay, so question number 5. What is the molar mass of sodium nitrate? So to find the molar mass of sodium nitrate, we need to know all the individual molar masses of the atoms in this compound. So to do that, we can find these values on the periodic table. So the molar mass of this compound will be the molar mass of sodium plus the molar mass of nitrogen plus 3 times the molar mass of oxygen, since we have 3 oxygen atoms in this compound. So the molar mass of sodium is 22.99 grams per mole. The molar mass of nitrogen is 14.01 grams per mole. And the molar mass of oxygen is around 16 grams per mole. So adding all these values up, we get a total molar mass of 85 grams per mole. So this is option E for the multiple choice. And the junior tutor said that the molar mass of individual atoms making up sodium nitrate is shown below. And they also got 85 grams per mole. So this solution is correct. Okay, so question number 6 asks, is nitronium NO2 plus polar or nonpolar? Okay, so first let's draw the Lewis structure for this ion. So we'll find the total number of valence electrons. So nitrogen has 5 and oxygen has 6. And since there are 2 oxygen atoms, we multiply this by 2. And also notice that our overall ion has a positive charge. So that means we need to subtract an electron from our total count. So adding these values up, we get a total of 16 electrons. Yep. And now we need to draw out a skeletal structure for this compound. So nitrogen will be our central atom. And I'm just going to draw 2 single bonds to the oxygens And let's show all the lone pairs and count out how many electrons I've drawn so far. So notice that we have our 16, but our nitrogen doesn't have a full octet yet. I'm just going to bring one of these values down to make a double bond. Okay, so now we have a structure that has also 16, but again, our nitrogen doesn't have a full octet. So let's draw another double bond to one of the oxygens. So now we have kind of like this linear structure. And this is where we find our positive charge. So let me show how we can calculate that charge by using the formal charge equation. This is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. For both of the oxygens, they have 6 valence electrons, 4 non-bonding electrons, so the lone pairs, and each of them have 2 bonds, so that means we have 4 bonding electrons divided by 2. So both of the oxygens will be neutral. And for our nitrogen, nitrogen has 5 valence electrons. There are no lone pairs in this structure. And there are 8 bonding electrons divided by 2. So this is how we know that nitrogen will be the one to carry the positive charge. Okay, so since we have a charge of this on this compound, anytime an ion is charged, we have a polar molecule. Okay, so let's see what the junior tutor said. A polar molecule is a molecule that has a dipole moment different from 0 because it has a non-uniform distribution of electrons. They found the electronegativity difference to be polar because it has a value of 0.5. And they kind of showed out all their steps. And determined the correct Lewis structure. And then noted that the bonds cancel each other out. So they wrote that the nitronium ion is nonpolar because of this. I'm just going to say that the explanation is correct. However, for charged molecules, they are considered polar. Okay, so question number 7. What is the shape of a carbon dioxide molecule? So first, let's calculate the total number of valence electrons, which will help us draw out a Lewis structure for carbon dioxide. Oops. So carbon has 4 valence electrons, and oxygen has 6. And since there are 2 oxygen atoms, we multiply this by 2 to give us a total of 16 valence electrons. So now let's try to draw out a skeletal structure. We can draw the carbon having 2 single bonds to each oxygen, but our carbon doesn't have a full octet, so each of these oxygens will be double bonded. And then I'll just draw in the lone pairs. And if I count out the number of electrons in this structure, where each bond contains 2 bonding electrons, we should get our total number of 16. So now to find the shape of carbon dioxide, let's look at our central carbon atom. The carbon atom has 0 lone pairs and 2 bonded atoms. So using a Vesper theory table, we can try to figure out its shape. So this is a Vesper theory table, and when we have 0 lone pairs and 2 bonded atoms, we have a linear molecular shape and electron geometry. Okay, so out of all the options they give us, this is option number A, or option letter A. And the junior tutor said that the shape of a molecule can be determined using the Vesper theory. What we need first to implement the Vesper theory is to write the Lewis structure of the molecule. They have the skeletal structure, and then showed the complete Lewis structure, and found that the molecule was linear. So this solution is correct. Okay, so question number 8. Compare the sizes of a nitrogen atom and a nitride ion, and explain. So a nitrogen atom is actually less than a nitride ion, which is N3 minus. So since N3 minus gained an extra 3 electrons, and we know this because it has a 3 minus charge, and electrons have a charge of -1, so it gained an extra 3 electrons. Therefore, its atomic radius increased making it larger than a neutral nitrogen atom. So a rule of thumb when trying to compare the sizes of different ions is that when you have a cation, which is positively charged, and it lost electrons, it tends to be smaller than our neutral atom. Again, since it lost electrons, its ionic radius decreased in size, but a neutral atom is still smaller than its anion. So anions are negatively charged, and it gained electrons. Okay, so let's see what Junior Tutor said. The size of an ion can either be greater or less than the original atomic size, depending on the charge of the ion. When a neutral atom loses electrons to form a positively charged ion, called a cation, the shielding effect of the electrons decreases, which attracts the electrons more to the nucleus, resulting in a smaller ionic size. On the other hand, when a neutral atom gains electrons to form a negatively charged ion called an anion, the added electrons will repel other electrons, resulting in a larger ionic radius. Okay, so this solution is correct. Okay, so question number 9 is look at the molecular orbital for O2. What is the bond order? And to increase the bond order of O2, should you add or remove electrons? And what is the charge and the bond order of the new species made in part B? So they included the molecular orbital diagram for oxygen, but let me kind of label it a little more. So I'll draw in all of the different orbitals here. And this is a good molecular orbital diagram, but it's kind of just missing some of the labels. I'm just going to quickly sketch it out. And this orbital here is the 2s orbital. And these are the sigma. (2s), and at the top is the sigma star 2s. So this sigma star refers to the anti-bonding orbitals of 2s. So now at the top here, we have our 2p orbitals. And we have the sigma 2p. And at the top here, we have our pi orbitals. So pi 2p. I'll just write it once so that it's not too crowded. And on top of that is the pi star 2p. And then at the very top is our sigma star 2p. Okay, so on the left and the right is a regular molecular orbital diagram for a single oxygen atom. So they have the 6 valence electrons drawn in. 1, 2, 3, 4, 5, 6. And since this is O2, we have 2 oxygen atoms coming together. So they're going to have the same molecular orbital diagram. And in the middle, we can show how they kind of bond together. So these 4 electrons can fit in here. And now we have the remaining 8 electrons to fit in the middle right here. So 1, 2, 3, 4, 5, 6, 7, 8. So let me write the bond order equation on the right. So bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons oh, it's cut out, sorry. So bonding electrons minus anti-bonding electrons divided by 2. So if we calculate the bond order of a neutral diatomic oxygen, all of our bonding electrons are in just the sigma or the pi orbitals, so we just count that out. So 1, 2, 3, 4, 5, 6. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding electrons minus 2. And 1, 2, 3, 4. So we have 4 anti-bonding electrons. So 8 minus 4 divided by 2 gives us a bond order of 2. And the second part of the question asks, to increase the bond order of O2, should you add or remove electrons? Okay, so let's look at our molecular orbital diagram. So to increase the bond order, the removal of electrons might be better since the orbitals for the bonding electrons are already filled. I'm just going to write that down. So for example, if we removed the anti-bonding electrons at the top, so let's say we had the bond order of O2 2-, then we would still have 8 bonding electrons, but this time we would have 0 anti-bonding electrons divided by 2. So then this would increase our bond order to 4. So for part B, removing electrons can increase the bond order. Okay, so now for part C, what is the charge and the bond order of the new species made in part B? Okay, so I calculated it already, and it would be 4. Oh, sorry, when you remove electrons, it has a +2 charge, so let me just change that. Okay, so this is D, B, and C in 1, so let me just write that here. And you get the bond order of 4. Okay, so let's see what the junior tutor said. So we kind of did the molecular orbital diagram together. They have the equation for bond order, but I think they counted out only 6 bonding electrons. One, 2, 3, 4, 5, 6, 7, 8. So I'm just going to fix that. And the anti-bonding electrons should be the ones that are sigma star or pi star. Okay, so this explanation is correct. However, the bonding electrons are located in the sigma and pi orbitals, whereas the antibonding electrons are in the sigma star and pi star orbitals. Okay, so I just kind of fixed the bond order equation. And can move on to the next question. Oh, that's all for today. Okay, so if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.